Welcome back to video 2 of the two-part SEM class video series from UC Berkeley's Marvell NanoLab. In this video, we'll be learning about how our substrate will interact with the electron beam to form an image. Electrons interact with the sample in multiple ways, depending on where the electron scatters in the material. The volume of the sample that interacts with the electron beam is called the interaction volume. If the electron scatters at the very top surface of the sample, it produces an Auger electron, which contains surface atomic composition information. You can also get secondary electrons or backscattered electrons if the electron scatters deeper inside the sample. These are the primary scattering mechanisms that we use to produce SEM images, and we'll talk about these more in a moment. You can also get characteristic X-rays, continuum Bremsstrahlung X-rays, or cathode luminescence, depending on where the electron interaction is occurring. The X-rays that are produced are the reason that SEMs are classified as radiation-producing machines. The radiation produced inside the tool is completely absorbed by the vacuum housing, and since the filament can only produce electrons in a vacuum, it is not possible to expose yourself to X-rays while the SEM chamber is open. Let's look at the interaction volume again. The size of the interaction volume depends on the accelerating voltage of the electron beam. At the very beginning of video 1, we saw that the wavelength of the electron depends on its voltage, and that higher voltage electrons are effectively smaller. This means that the chance that a higher voltage electron will scatter in the substrate is also smaller. Higher voltage electrons travel further into the substrate before scattering, making the interaction volume larger. The material itself also matters. If the sample being studied has few electrons, a low atomic number, there are fewer chances for scattering to occur, regardless of the accelerating voltage of the incoming electrons. Lower atomic number materials will also have larger interaction volumes and deeper substrate interactions. Now that we've discussed the interaction volume, let's take a closer look at the secondary electrons and backscattered electrons. Secondary electrons occur when you have an inelastic collision between the incoming electron and the electrons in the sample. The incident electron provides enough energy to eject an electron from the sample atom, which can make its way to the detector. If the ejected electron is an inner shell electron, an outer shell electron will fill in the vacancy, giving off a characteristic X-ray, which can be used to identify the composition of the material as well. Backscattered electrons occur when you have elastic collisions between the beam electron and the nuclei of the sample atoms. This is more likely to occur with heavier nuclei, which can allow you to distinguish different elements just by looking at the contrast of the image. This is an example of that from the Australian Microscopy and Microanalysis Research Facility. The left image is a backscattered image of sand grains, while the right image is a secondary electron image. There is a subtle difference in the intensity of different grains in the left image, while the right image is more uniform. The researchers were able to use the known composition of the sand to distinguish between grains made up primarily of silicon and grains made up primarily of titanium. Another common substrate interaction effect is the edge effect. As the beam traverses a feature with some height change, more of the interaction volume comes close to the edge of the sample, which will allow more electrons to escape the material and reach the detector. This means that edges of features typically appear brighter in the SEM image. Another issue, and typically a frustrating one, is charging of your sample. While the sample stage is grounded, insulating samples will tend to build up charge, making it difficult to get clear images. You can minimize charging by reducing the beam current to allow electrons time to reach the ground. If your insulating material is thin, you might want to increase your voltage so that your interaction volume penetrates to a more conductive layer beneath your insulator. However, if your substrate itself is insulating, this might not resolve the charging, in which case you may need to add a conductive layer to the top of your sample in order to image it. This is the conclusion of SEM class. You should feel comfortable with the roles of the different components of the SEM. You should know the terms working distance, astigmatism, interaction volume, secondary electrons, backscattered electrons, and you should be familiar with how to deal with charging. You may now take the SEM class exam to get credit for watching these videos.